All right, so we're on. So the Medicis, or Torricelli, discovered one form of pressure, but we have a number of them. So we're going to start with the different things that equal 1 atmosphere. Okay, the first one is 101,325 pascals. We talked about this earlier with the baseball sitting on the coffee table. This is a big number, so we tend to not use, go ahead and close the parentheses there. We tend to not use pascals like this. We use our metric version of Pascal, which is going to be the kilopascal. And so atmosphere is also 101.3 kilopascals, kPa. It is also 14.7 pounds per square inch. It is 760 millimeters of mercury. This is the value that Torricelli found, the 760 millimeters of mercury, or 76 centimeters of mercury. Same value. Okay, and that's also the same thing as 29.9 inches of mercury. And this, the inches of mercury, the barometer's at 29.5 and falling. At the weather report, it's measuring in inches of mercury. Again, because we're American and we can't quite get a grasp on the metric system. So, this 760 millimeters of mercury, this millimeters of mercury is actually named after Torricelli, and so it is also called a torr after Torricelli. Okay, 760 Torricellis is just too long of a word to say, so we called it a torr. All right, there's another term, the 100,000 pascals, okay, or 100 kilopascals is called 1 bar, which is a meteorological unit. 1 bar is 0.9869 atmospheres. Now, these may be used as conversion factors. So, we are going to convert our millimeters of mercury into pascals using our new conversion factors. We are going to start with 460 millimeters of mercury. In fact, let's expand this a little bit.
Ours is already worked in.
Oh, it's already there?
Yeah.
Who? Okay, well, let's work it anyway. This is 460.
Yeah.
460 millimeters of mercury. Times, we want to go to pascals. We know that 760. Okay, guys, I don't understand why we're talking right now. Okay, you guys already have writing right there. We're going to work it through anyways. Okay, 460 millimeters of mercury, but we know that 760 millimeters of mercury equals 1 atmosphere, or 101,325 pascals. And then we multiply that out, and we multiply that out, and we get
61,350.
that. Okay, we get 61,328 pascals. Okay, and then we can do the same thing with 25 pounds per square inch. Okay, turning in inches of mercury. We start with the 25 pounds per square inch. Divide by 14.7 times 29.9 is going to give us our 50 inches of mercury. You guys are going to be expected to do that. To convert between pressures. All right. Okay, bringing us to properties of gases. Oh, by the way, it's at this point that I want you guys to summarize 13.1. So I'm going to pause. Okay, so after you summarize, we're moving on. So, properties of gases. First, we have compressibility. Gases are compressible. This is a measure of how much the volume of matter decreases with an increase in pressure. Okay, gases are highly compressible due to the large distances between the molecules. Okay, but we did that last Friday when we did the matter dance. Remember that the distances between the particles were large. The particles themselves are actually small. Okay, solids and liquids then are only slightly compressible because of the close distances of the particles to begin with. They're tightly packed. In liquids, they're still tightly packed, but they're still moving past each other. For example, 1 mole of any gas at STP has a volume of 22.4 liters, but that same mole of water, liquid water, has a density of 1 gram per milliliter. Okay, well, if water, H2O, has a molar mass of 18, and it has 18 grams per mole, and every gram is 1 milliliter of water, then 1 mole of water is actually going to be 18 milliliters. Okay, so think about this. You take this 18 milliliters and you boil it and you completely turn it into vapor. Okay, it's going to expand to 22.4 liters. Okay, then sometime after at lunch or after school or something, if you want to hear about the microwave bomb, come talk to me. Yes, Dave.
It says 18 blank over mole.
Grams per mole. That's the molar mass of water is 18 grams per mole. Stop. I said ask me at lunch or after school. Okay. Factors affecting gas pressure. The amount of gas is one of them. So as you double the amount of gas at the same temperature and volume, the pressure doubles. Okay. The volume affects gas pressure. As you expand a gas to twice the volume at the same temperature, the pressure is halved. That kind of makes sense. If you keep everything the same, you give the same amount of gas more room, then you're going to have less collisions against the wall of that container. Okay. Temperature affects gas pressure. If you double the temperature of gas on a Kelvin scale at the same volume, the pressure will double. Okay, so those are the effect of various effects on gas pressure, which brings us to the gas laws. Now we talked about we saw the video on this on Monday. Okay, the scientists that Dr. David L. Goodstein talked about on Monday he talked about Robert Boyle, and The three French names. Last name was Charles. Then we'll get to the other guys. The gas laws are the mathematical representations of the observed relationships among pressure, volume, temperature, and the quantity of a gas, also known as P, V, T, and N. Okay, this N stands for the quantity of the gas. Alright, so our statement. Boyle's law. This is what he said Boyle's law. This is what he said the law was. It's a lot of writing. When the temperature and number of moles of a particle are fixed, the pressure-volume product yields a constant value. It's a really convoluted, sciencey way of saying P times V equals a constant. Pressure times volume equals a constant. So if one goes up, the other one goes down. This is considered an indirect relationship. So the expression, okay, the other expression of this is P1V1 equals P2V2. So whatever pressure and volume you have to start is going to equal the pressure and volume, pressure times the volume when you finish. Okay, what things are assumed to be constant? Temperature and the number of moles are held the same. If you don't change how much gas you have, and it's all done at the same temperature, if you increase the pressure, you're going to decrease the volume and vice versa. Okay, Robert Boyle was among the first to observe the properties of air. He trapped a fixed quantity of air, added pressure, and measured the volume change. Okay, when the pressure increases, the volume decreases, and vice versa. This is an indirect or inverse relationship. Double the pressure, the volume is halved. To triple the volume, the pressure needs to be thirded. Or you have to have 1/3 of the pressure to triple the volume. Aye?
Aye.
Thank you. Okay. So, suppose we're on two trials of a fixed gas for a set temperature. Since PV equals a constant, we'll call it K, then P1V1, the first set of conditions, okay, is going to equal K, and P2V2, which is a second set of conditions, is also going to equal K. So, because they equal the same constant, the two of them equal each other. That's how we get P1V1 equals P2V2. So if we know three of the four values, we knew two of the pressures and one of the volumes, or any one of those three things, we can calculate the rest of them using cross multiplication. If you do not know how to cross multiply, now is the time to learn. So our example, calculate the final volume of a 250 milliliter balloon at 25 degrees Celsius when its pressures change from 740 to 850. Okay, so what things do we know? Don't just go and look at the answer right now. We know that this is 25 milliliters is going to be a volume, right? But this says final volume, so we're going to call this one P2. Okay. If it is changed from 740 to 850, so over here we got a pressure change from 740 to 850. 740 is going to be which one? Is it going to be P1 or P2? This is going to be P1 equals P1. And this down here is going to equal P2. Sorry, this is not P2 over here. This should be V2 over here. Good catch, you guys. That's going to be V2. So, what we need to do is figure out what V1 is. We have P1, we have P2, we have V2, we don't know V1. And so, we solve it like this. P1 V1 equals P2 V2. Okay. Or V1 equals P1 V1 over P2. Do we see how we go from here to here? No? Okay, we need to divide by to get V1 by itself. Oops. That's wrong. Poo. Okay, so yeah, that was wrong. These should be V2. These should be the 2's on top. That should be a 1 on the bottom. And that's how we solve for V1, which is what we're really looking for. Okay. Then once we have P2 V2 over P1, we plug in these values. The 740 millimeters times okay, I totally want to rewind that because I was right to begin with. Except I was wrong to begin with too. This is V1. This is V1. This is V1, P1, P2. Okay, we know V1. This is still screwy. This should still be V2. This should be V2. The other ones were right. If you label everything correctly, which I didn't do the first time, then you plug them in, you're going to get what your final volume is, which in this case would be 218 mils. And